So for this problem, we have 2.25 kilograms of refrigerant 134A at initial pressure of 8 bar and temperature of 60 degrees C. It undergoes a process to a final state having a pressure of 2.8 bar and temperature of 40 degrees C while being rapidly expanded in a piston cylinder assembly. Heat transfer between the refrigerant and its surroundings occurs at an average temperature of 50 degrees C. That's going to be important for second law analysis. The work done by the refrigerant is 50 kilojoules. Kinetic potential energy effects can be ignored. Determine the heat transfer for the process. That would be like Q 1 to 2. And then the entropy generation for the process, I'll sometimes write Sgen because it's hard to write a Greek symbol sigma, which the book uses, sigma 1 to 2. They don't use 1 to 2 for the subscripts. I just like to add that. So either one of those notations is good for me or you. All right, so let's go ahead and think about organizing the information given. So we'll have a mass of 2.25 kilograms. I like to put any property data in a little table. So we'll put pressure. I like to put kilopascal. It doesn't matter. You can put bar, degrees C, and then we'll go ahead and say what state we're at. State 1 and then state 2. We're starting at, well, let's leave it in bar. Really, there's no advantage here. It's 8 bar. And 60 degrees C, and 2.8 bar, and 40 degrees C. And we're going to be interested in other properties. We're interested in calculating the heat transfer during the process, so that's probably going to require us to use the first law. And then we're interested for part B, the entropy generation or production. That'll be the second law. Well, what does the first law look like for a process? Well, it'd be like the mass and the change in specific internal energy. So going from 1 to state 2, so m times U2 minus U1 is equal to the heat transfer during the process minus the work 1 to 2. We take a look, and they gave us the work, didn't they? And so the work 1 to 2 was 50 kilojoules right here. And so it's like, this is known, this is what we're trying to solve for. The mass is given right here, 2.5, and we need the U's. So in this organization for a table, we'll set another column, U in kilojoules per kilogram. We've done property evaluations for refrigerants before. We go and take a look, and we find that, oh, it's going to be in a table A12, for superheated a refrigerant 134A, and we could look up internal energy 271.04. And while we're at it, let's go ahead and get S in kilojoules per kilogram Kelvin. The entropy, it's right next to it, 1.0034. And then at this pressure of 2.8 bar and 40 degrees C temperature, we pick up 260.17 and 1.0494. Again, where did they come from? Table A12 in the book. It's for superheated refrigerant 134A. Okay, so it's like we just were able to get this one and this one. So we can solve for Q 1 to 2 is equal to the work 1 to 2 plus the mass U2 minus U1. So we'll put in our 50 kilojoules plus 2.25 kilograms times 260.17 minus 271.04 units of kilojoules per kilogram. The kilograms go. We're left with units of kilojoule, and the heat transfer during the process comes in at 25.5 kilojoule. Answer for part A. Okay, so now we're going to use the second law to get the answer for part B. What does it look like? Well, the change in the entropy It can go up by having a heat transfer that brings with it across the boundary of the system an entropy. Now, because I use this interesting wording that the surroundings occur, the heat transfer between the refrigerant and the surroundings occurs at an average temperature of 50 degrees C. What they're really telling us is that TB is 50 degrees C. It's our boundary temperature. Now, when we put it into this equation here, we have to have it in absolute temperature scale, have to have it in Kelvin. So we'll add 273 and we'll get 323 Kelvin. I'm not going to put the 0.15 on there. It's close enough. So we're going to use 323 Kelvin. Okay, and then the other term that you have is you have an entropy generation, a sigma 1 to 2 in our textbook. Okay, so it's like this is what I'm asked to solve for. It's my entropy production due to irreversibilities. I just calculated Q1 to 2. I've got the TB was given to me. I converted it into Kelvin. Out of the tables, we got the S's. They were given the mass, and so it's pretty straightforward. So let's solve for sigma 1 to 2 is equal to MS2 minus S1 minus Q1 to 2 divided by TB. So we'll put in our 2.25, and then our final entropy 1.0494 minus 1.0034, then minus our 25.54 kilojoules divided by 323 Kelvin, and then sigma 1 to 2 comes in at 0.244 kilojoules per Kelvin. That's the answer to part B.